So this week we're discussing synchronization. So we know that processes can execute concurrently on the system, and because we have multiple processes and we have limited number of CPUs, processes can be interrupted while they're running and before they complete their execution, right? And so cooperating processes or the processes who share data together may actually be interrupted while operating on that shared data, right? And so if we do not have some certain mechanisms or strategies to synchronize access to those shared resources or shared data, we may end up with some data inconsistency. So we've seen this example before when we talked about the producer-consumer problem. So the producer is a thread that produces an item or writes into a buffer in this scenario, right? And the consumer on the other side reads that data from that buffer, right? And so since this is a shared buffer between these two threads, if we don't have proper synchronization tools implemented, then the consumer may read some data, may read this shared buffer while the producer is still writing to it. So we can have some problems with data consistency in this scenario. So to further explain the motivation behind synchronization tools, think of a variable that's called count, which is currently equal to 5, right? Assume that the producer and consumer processes, they are currently concurrently executing, right? And one is trying to increment the shared counter, and the second is trying to decrement it, right? And so we would expect the only correct result to be equal to 5, no matter what the order is. So if the increment happens first, so we're going to go from 5 to 6, and then we're going to decrement back to 5. Now, if the decrementation happened first, then we're going to go down to 4, and then we're going to increment back to 5. So the only correct possible result should be 5, right? Now let's take a look at this simple incrementing operation or task. So if we look in low language or machine language or assembly, the simple count plus plus or increment actually consists of these three elementary tasks. So we would save the value of the counter in a register called register 1. And then we will add this value. So in here, we're simply incrementing by 1. So register 1 will be updated to register 1's old value plus 1. And then finally, we will load this new value of register 1 to the variable count. So we got 3 steps right here to simply execute this count plus plus, okay? So imagine this possible scenario where the producer starts executing here, right? So I'll start by this first task, which is register 1 equal count. So now register 1 equals 5. And then next, the producer is still having hold of the CPU, and it will proceed to the next line or the next command. Now we add 1, so register 1 is equal to 6 at this point, right? Assuming at this point, for some reason or the other, the producer got interrupted by the consumer and the consumer starts executing. So the consumer will start on the other hand here on the first line of its own code, right, which is the decrement operation. So register 2 equal count. Now register 2 has 5. And then the next one right here is register minus 1. So now register 2 has the value of 4. Assuming that before it gets to the last line, it gets interrupted again by the producer. Now the producer stopped at this point, right? So it'll continue executing its last line. So count equals register 1, right? So now count is 6. And then at that point, it gets interrupted by the consumer again. And the consumer already stopped here last time. So it will continue again to the third line, which is count equal register 2. Now count has a value of 4. So 4 here is an incorrect outcome because we said the only correct value should be 5. And we ended up with a wrong value because of this concept of interruption, right? These processes kept interrupting each other, and we had no mean of synchronization in between. So what we just saw here happening to this shared variable is called race condition, right? When we have multiple processes or threads that share access to one resource or piece of data, and they're all trying to access it at the same time, and then the outcome or the result depends on the order, right, for which these accesses happen or took place. So that's what we call race condition. The only possible solution is to only allow one process to make the update to the shared resource or to manipulate it at a time, okay? And to do that, we need some synchronization tools. So another example of the race condition is the next available PID kernel variable. So this one, so remember we talked about how each process is identified by a unique PID, right? So let's say we have two processes, right, that were just created using the fork system call. So these two processes will execute in concurrency, and they will both try to access this kernel variable to get a unique PID. So if we did not have proper synchronization tool, then we may end up with these two processes getting the same PID assigned, which violates this requirement of having a unique PID. So we define a critical section problem by that section or segment of your code where this race condition may happen, where we have multiple processes or threads that are trying to manipulate a shared resource, okay? That's the critical section, okay? And the critical section problem is trying to synchronize or solve the critical section by using some means or tools of synchronization. So it usually consists of these main subsections, right? So we always start by the entry section. So remember we said that the only solution is to only allow one process in the critical section at a time. So only one process will be manipulating that shared variable, okay? So the critical section is what we're trying to protect, and this is where we have that shared count plus plus, for example, happening, okay? This is what we want to only allow one process to access it at a time. So to do that, we start by an entry section where each of the concurrent processes are requesting access to the critical section. They are announcing that they're ready to enter the critical section, and they are requesting permission, okay? Once allowed, one process will execute that manipulation of the shared variable. Once it's done, the executing process has to announce that it's currently done from the critical section, and it's exiting, and it's allowing any other waiting processes to take their turns, okay? And then at the end, we have this remainder section where you can have all the other instructions of code that do not deal with a shared variable